Hi, this is the second of the Banana Lab videos. In the first video, I introduced you to the lab equipment and the type of techniques that you'll be doing in lab. In this video, what I want to do is show you some of the calculations that you'll need to do and also give you some of the drawings that you'll need to do on your handout in the pre-lab on the handout before you turn it in. I've got several molecules on this slide. The top two on the left are glucose and fructose. You might remember that those are monosaccharides, in that they consist of one unit of 5 to 6 carbon atoms. Down here we have sucrose, which is a disaccharide. Basically it's two monosaccharides joined together. Whoops, saccharide, there we go. And you might wonder, well, how does that happen? In a chemical reaction, what can happen between glucose and fructose is we can have a condensation reaction. You might recall that a condensation reaction means that we have a water molecule given off. So the OH that you see in red here and the H here combine to form water, so they leave and become water. And that leaves some bonds that can join together. So once the OH is gone, there's a carbon here which now only has 3 attachments. This has to attach to something else. There's a carbon here and an oxygen here, and that oxygen has one attachment to the carbon and another that was on the H, which leaves it an attachment. So the oxygen from this molecule can attach to the carbon over here, and you see that right here. Here's this O attached right down here between the two. That's called a glycosidic bond when that happens. Now that glycosidic bond can occur over and over and over again, and when it does, you get a polysaccharide. You might think about another glucose molecule reacting with itself. So here we have 2 glucose molecules, and if the OH on one combines with the H of the other in a condensation reaction, then you can see you can form the glycosidic bond here. If we had another glucose molecule over here, the H could form with an OH and we'd have another glycosidic bond, and you can keep going and going and going and end up with a very long chain molecule known as a polysaccharide, and in this case the polysaccharide is a starch. In the banana lab, we will look at the amount of starch in bananas, and starch is an insoluble substance. It doesn't dissolve in water. Those OHs that are very polar in the glucose and the fructose and the sucrose, which make sucrose and fructose and galactose all soluble, are gone in the polysaccharide because everything is joined together and you've got this long chain molecule that's basically nonpolar. So molecules that go together by condensation reactions can also go apart by hydrolysis reactions. In a hydrolysis reaction, typically you have an enzyme. Here's a very common one. If you're lactose intolerant, you don't have the enzyme lactase, and that means that you're not able to break lactose apart, which then results in some discomfort and cramping possibly because your intestines can't absorb the molecule lactase. If you have the enzyme lactase, what happens is it breaks this bond with the help of some water, and I should have actually drawn the bond, circled the bond instead of the O. But basically it breaks the glycosidic bond. The water then joins in, so where we took out water before, we're going to add water back in. So we can add an H on one side and an OH on the other side, and we can get 2 separate molecules, in this case galactose and glucose. So in a banana, there's various enzymes that are at work as the banana ripens, and one of those enzymes is called amylase. Amylase has the ability to break down starches into glucose. If you've ever had a cracker in your mouth for a long period of time, you might notice that after a while it starts to taste a little sweet. That's because an enzyme in the saliva in your mouth is breaking down that starch into its individual monosaccharide units. Here's some calculations that we'll be doing in lab. you're going to have some solution in a flask. The solution is going to be the banana extract, where you have separated the soluble glucose from the insoluble starch. So you've got your glucose in this flask. Now we're going to measure that glucose using something called a glucose test strip. And our glucose test strips read in milligrams per deciliter. What we want to do is change those units, milligrams per deciliter, to grams per milliliter, so that we'll be able to do a calculation to figure out the percentage of glucose that's in this flask. Okay, so let's say we've tested our glucose. We found out that we've got 500 milligrams per deciliter. And what I want to do is change that to grams per milliliter. Here are some conversion factors that I can use. There's 1,000 milligrams in a gram, and a deciliter is the same as 100 milliliters. So, working the problem, 500 milligrams for each 1 deciliter. Make sure you write it like that, with the milligrams on top and deciliters on the bottom. Remember, when we have fractional units, we don't just put it over 1, we put the numerator on the top and the denominator on the bottom. Okay, so we want to change our milligrams to grams. Here's our conversion factor. The milligrams has to go on the bottom so that it'll cancel, and that means our 1 gram goes on top. That way our milligrams now cancel. If we stopped here, we'd have grams per deciliter, but that's not what we want. We want grams per milliliter. So our next step is to use our other conversion factor here. I'm going to have to change my deciliters, which is over here. I want to change that to milliliters. So in order to do so, I got to cancel that deciliters, which means my 1 deciliter has to go on top here, and my 100 milliliters on the bottom. That way we get the deciliters over here, canceling with deciliters over there. When I do the calculation, 500 divided by 1,000 divided by 100 will give me 0. Let's see, 5 places, 0, 1, 2, 3, 4, 5, 0, 5. And notice my units that are left, grams over milliliters. You know, that's just a regular density unit, right? So essentially the density of the glucose in the solution is 0.005 grams per milliliter. Now, let's say that I measure this solution, and when you measure this solution, you don't want to just read it off the Erlenmeyer flask here, because Erlenmeyer flasks are very inaccurate. You're going to put this in a graduated cylinder, and you're going to read your graduated cylinder to the nearest tenth or the nearest 100th, depending which cylinder that you use. So I put this in a 100 milliliter graduated cylinder, which means I can read it to the nearest tenth, and I found out that I have 24.5 milliliters of banana extract. What I want to know is, how many grams of glucose is that? Here's my grams of glucose for each milliliter. I've got 24.5 milliliters. If I just multiply those, I'll be able to calculate the grams. So I take my 24.5 milliliters from here, multiply it by my conversion factor here, which is 0.005 grams for each milliliter. The milliliters are going to cancel. 24.5 times 0.005 I calculated already, and it turns out that that is 0.1225 grams. Okay, so in my liquid here, there's 0.1225 grams of glucose, and I extracted that glucose from a banana chunk. My banana chunk, when I started, had a mass of 3.6 grams. So let's figure out the percent glucose then. It's an easy calculation. We do the part divided by the whole. So we've got 0.1225 grams of glucose, and it was in a total amount of banana that was 3.6 grams. Dividing those, I get 0.034 something. I had it on my calculator and unfortunately it's gone right now, but I remember it was 0.034 something. So then to change that to a percent, move the decimal point 2 places to the right, and I end up getting 3.4% glucose in my banana. Hey, so Scout and I are done for now. It was nice talking with you. When you're in lab, you'll also have to do a percent starch calculation, but it's very similar to the percent glucose calculation. And I think this is a really fun lab. I'm looking forward to seeing you. Bye.